Okay, let's just get it started. Today we're honored to have Dr. Fang from NYU to be our speaker. Dr. Fang is a professor, engineer, and entrepreneur specializing in embodied AI and robotics. He directs the NYU Embodied AI and Robotics Lab, where he leads research in AI-driven perception, reasoning, and action with applications across engineering, healthcare, and beyond. He also serves as the co-director of the Center for AI and Robotics and the co-director of the Center for Interdisciplinary and Data Science at NYU Abu Dhabi. Dr. Yi Fang holds a bachelor and master degree from Xi'an Jiaotong University and a PhD from Purdue University. His contribution to AI and robotics have earned his recognition from the U.S. National Science Foundation and UAE Abu Dhabi Department of Education and Knowledge. In addition to his academic leadership, Dr. Yifang is a co-founder of ChatSun Technology, a company developing generative AI-powered assisted devices that support communication for deaf and hard of hearing individuals. He also founded EZ247 AI, an agentic AI company dedicated to connecting customers and service vendors with efficiency and effectiveness. Dr. Yifang actively contributes to the broader AI community, serving as an area chair for leading conferences such as CVPR, ICCV, ECCV, IROS, and IJCAI. His dedication to advancing AI research and technology transfer reflects his commitment to fostering innovation that benefits society. Let's welcome Dr. Yifang to start his seminar.
Thank you so much for invitations, and thank you for your introductions, Professor Wang. First, can you guys hear me, and can you guys see the slides? All good?
Yes. Yes. Everything's
Okay.
good.
Today, thank you. Today I or talking about partially the work that we have been completed over past roughly less than a year. So this is not going to be very comprehensive talk, but rather being a conversation with the group here for my thoughts regarding this navigation, particularly for embodied navigations. So so what is the embodied navigations? When you're what is the difference between this embodied navigation and the navigation we always talking before? So the difference is the ability of the intelligence agents to perceive and interpret. The most important is to interact with their own environments to achieve the goal-directed movement. So this is very essential definition for embodied navigation part. It's not only perceive, it's not only capable perceptions, and we also has it has to be understand their environment's context. The most important part, it allows lots of the sequence of their interaction with the environments to complete the goal. So if you look at the traditional one of the like if any robot is going to be lacking navigations or there's no environmental understanding, a lot of cases most likely people is going to be using the menu, the remote controls navigations to guide it, and the robot agents move in a certain environment. So this is a lot of the issues for doing that. For instance, their remote connection is not stable. It's be a lot of issue. So in order to make this, the agent has the ability to navigate by its own. It has to have a certain ability to perceive to the gathering their environmental information by its sensor. For example, it's their audio sensors, their videos, the vision sensors, and their distance or measurements and depth sensors as well. A lot of sensors it's been gathered by its own body sensories. And the next important part is from the sensory to actions. They need to interpret to understand the environmental context. So to have a certain high level, semantic levels, understand the environments to help them make the following directions and then the actions that pursuing their navigation driven by completely certain goals that we're going to discuss in this talk. So why it's important is in order to enable the agents handle world's variabilities. So because the world is very dynamic, variables, obstacles, it's not static, it's not clean. So it's a lot of the dynamic obstacles along with important things is the task that the agent is going to finish. It's somewhat very complex. It's not a single directed goal-driven task. So in order to make the agent adapt to this very diverse real-world environments, conditions very effective, and also the agent should be navigate with moving around moving dynamic obstacles very safely and seamlessly. An agent should be very performed complex task with precision and efficiencies. So this is putting a lot of the high standards for this embodied agents to be able to navigate in to satisfy the certain real world environments at least partially here. The core important part for any this embodied agent to navigate, it's going to be perception part. It has to be extremely powerful perception, and also has to have a good planning to understand the world dynamics. That it's most likely have a good world model for having a good planning for the state transitions, and also important to have a good policy that's given the current state, what is the most variables, the actions that you're going to select it in order to make sure the final task reward is going to be adding higher expected values. So this is a very important two parts, the three parts, given a good, strong sensory perception in these cases, and then have very strong planning and very good policies, though, to make sure that the whole trajectory is being selected, that it's going to be achieved a good reward at its expected values here. So the embodied navigation, normally we had four different category, and with a bit more advanced subtask. So they could be indirectly based on dialect. So the engaging with conversations with the humans, or a conversation with the peer, the robot as well. They also could be just directly follow their instructions. So still, okay. That's another one. It's going to be given the point, navigating the specific coordinates or landmarks. The last one, which is going to be one of the focus today, it's object goal driven. It's going to find out the specific objects in the environment. There's two and more advanced subtask, which is going to be room navigations. You're going to be navigating a certain specific room that requires to be more semantic understanding for the room layout and object context. Another one, it's more challenging. It's instance goal navigations. It's going to locate it a very specific instance of an object. For example, the instance is given by an image, and then at random views. So you're going to be just showing that instance through those agents. Sorry, showing a instance with the picture showing the objects. That's how you're going to find out that instance in the unknown big environment automatically. So that's a pretty advanced topic that we're going to discuss today as well. So three main area for today's talk. One is going to be the object goal navigation. So it's navigating to a specific object. For example, object class. For example, find a bet. So given the find a bet, you need to find out any bet in the showing the environment by its own. Second one is instance image goal driven, image goal navigation. It's going to locate the very specific instance of an object using the image query. For instance, find out my mark, but this is not given by the sentence. It's not given by the text. It's given by one of the red mark image. And then they're going to search in that object showing on that image. So the very interesting part, which is very active ongoing goal for our lab, it's navigation dreamer. So it's leverage the generative models creating dynamic scenes representations and the word modeling part that is enable the robust first. It has to be pretty long horizon planning by representing the environmental dynamics. So we are just starting this research, but I think it's going to be holding a lot of the potentials for any collaborations for pushing the navigation in the next levels. So I'll be more open to discuss about these parts after the talk. Okay. The first part for the goal driven object goal driven navigation, it's also not so old. It's very new topic in this area. Like in the entire embodied navigation is pretty new and smaller area. So it's still a very active area. In order to having those object goal navigations, first approaches, it's for sure it typically perform the well-trained environment where agents can rely on the learned object features and spatial layout. So this is very it's very similar like our supervised training part. So given a good layout for the environment, given a certain category of the object in the environment, and then the navigation is going to find out this, and the agent is trying to find out the places and the objects. This is for sure, it's easy to present in lots of the issues for limiting in their abilities to be adapt unseen conditions or their new object categories. So in order to have this kind of zero shot object goal navigations, like the better grounding the object based on the semantic meanings, the first things as all of researchers think about is using the foundation models, particularly for the at the beginning of the large language foundation models, because that model has been performs pretty well for this open vocabulary for their objects being grounded in this environment. So it's been designed to navigating unfamiliar objects in unknown environment, even though those not encountered during the training. But given the ability of the foundation models, language foundation models, they're capable of having those semantic or text groundings pretty well in this unknown environment. So it's going to be a bit more achieve the flexible generalization throughout semantic reasoning of the models, knowledge transfers, and ability, object affinity models as well. So it is not going to be heavily rely on the environment's specific fine tuning. It's going to reduce the needs for that part, given the very nice generalization ability of the foundational models at the level of the semantics descriptions. So the immediate sort of the shortcoming for this part is that when we started working on this on the earlier of this year, last December, we find out this is if you only based on those language model as a zero shot for the language for the object groundings, it's going to be presented certain issues here because critical challenge is written out, but where the object might be based on prior knowledge in their environment of the context. So the issue is like this. It's very strong ability, a reasonability, but it's not really having a good spatial infos. So this is very important. Whenever you are model this environment or the environment, the world as a very strong sort of representations, if you only based on the object or the semantic meanings or the text descriptions, you often having less representation, the features representations, less spatial informations being captured. So the first try for sure is very straightforward, replacing those large language model with vision language model part. So it's going to be have a better spatial visual informations in these cases. So instead of sending those language descriptions to a large language model, we send, as you can show here, we directly sent image description, the image to the vision language model to replace that part for the frontier selection, which means you can interpret for the actions that you're going to move for next step. So this is a very straightforward try, and then it turns out it works. It's improved performance a lot. That is actually predictable, right? Because the large language model indeed not really having a good spatial infos, well as this image, if you directly using the perceived image to those vision language models, it's going to be getting better results. So you can see the experimental result. For example, if you want to find out those TV, then in unknown environments, and then you're going to see their pathway relative, not going to be too much zigzag as is shown here, right? So this is going to be lots of the go back and forth, and this is going to be lots of the zigzag or wandering step for those for this original language-based language foundation model-based. Whereas if you've seen those vision language models parts, it's getting a clean pathway, so it's going to be much more efficient in the cases at a short pathway, and then have less trial for the searching part, for the searching the object. So then the smaller papers we're going to try right after this, it's for sure it's going to be, we immediately find out the vision language models. It's similar to those like large language models, a lot of hallucinations here. Therefore, there are causing issues for the reasoning part, which means reasoning part, most likely reasoning part is going to be impact for the frontier selection. Then it's going to consequently impact for the actions. So for examples, right? So if you can see here, and if you only based on one of the vision language models, which means I have been observed living rooms and the kitchen rooms. So just room interpretations. Since the target is microwave, and it's important note that the microwave is not commonly found out in either of the living room or the kitchen room. So this is something wrong because vision language model in that cases is not really that accurate. So therefore, they're going to miss the object. So the missed object to find out microwave in those kitchen rooms because they think it's not in the kitchen rooms. So to fix this part, I mean, we have lots of the solutions. MLE is one of the solutions. So say, in order to enhancing this reliability for this foundation models, then we're going to be using the multiple experts. For example, we're going to be having those objects to frontier experts, room to frontier the experts. We also have this scene layout, like the multiple relation among different objects. So if you are using those multiple those experts to do this reasoning parts, you do find out improvements along these lines. You're going to see the result here. So if you're using a single type of the expert multiple times, you run the majority common sense, you find out it's going to be weak if you have multiple diverse object experts to run the common sense. So this is a very interesting font as well. So if you're choosing multiple, for instance, 5 different experts, but it's all do the room or do the objects, instead of you having different type of experts, you find out the results are indeed you need diversified. The expert is going to be getting better results here. So after we having this is one of the example we did in this our one of our faculty buildings. It's apartment that we're going to find out where is the garbage can, and then there are getting we had this culture bet. It's the big culture bet has been running on those apartments. You're going to see they're going to be wandering in different rooms, and then they're going to find out, oh, this is going to be living room. And most likely it's going to the kitchen room as well. So they're going to make a mistake there because they find out that if they go over from that direction, they actually find out it is there. So this is going to be the trash can that we hide it in somewhere. But at least they're not going to be moved. They're not skipping this room because they find out the kitchen counters. They're going to stay here and search for this object they're going to be they're looking for, right? So it's very interesting that this culture bet, it's in the end it's going to find out objects in the real test environment. So this is it's a good sort of the prototype initiative effort within the very smaller incremental to this field. So and after we have those experience, then we think we had some papers been sent to the NEURPS 2024 and then accepted. So this is a very interesting study that when we're working on the object goal driven, we found out the object is mainly stay at the category levels, which means a chair is a chair, a desk is a desk, and the bed is a bed. Whereas based on our previous experience in computer visions, right? So lots of the objects should be has for object for the robotics application. The might be has 2 things very important. One is affordance. Another one is the it's multi-scale geometry representation in a sense like the parts, the different parts of the object. For instance, for a chair, they have the back seat, they have the seat, they have the legs. So the first affordance parts, it's very important because we're going to talking about this for any world modeling parts. So physics informed is always one of the most important the feature representation that is we often been omitted. So we don't have integrate a lot of the physics influence things in those navigation or any other robotics task, whereas that is very important for robotic intelligence part. The second part is motor skills. This is also important for those navigation parts. For example, why it's important. If you want to navigate, find out the words chair, but in a very dynamic environment. So you often has been a chance been occluded. So you might only see very part of this object, not able to identify the or not actually not observed the entire object. So it's a very smaller part. Maybe in this case, it's a very say small of this very small of those back seat, very partial. So if you only put in those object goal driven, this mean chair, it's going to be difficult seeing this is actually a chair. Then you're going to miss this is the chances of the you find a chair. So that's the main contribution of this paper. Instead of searching a chair, we actually having the multi-layer, multi-scale, and multi-layers representation of the chair for the different parts. For example, instead of searching the chair, we understand there are going to be chair legs, chair back, and chair seat. Then hopefully they're not going to be skip this direction, as well as moving this direction, find out where's the chairs. So and then finally you're going to move towards the chairs, find out these parts. So this is also naturally presenting the better ways to find out the layout. If you have the graph structures here, they're going to represent it with the object and its neighbors. So which is not yet finished in this paper, but it's in coming papers as well. For example, if you find the table, it's highly likely it's been associated with the chair, then any part information of the chair is going to be naturally propagating to those tables that we are going to be identified as well. So how do you do this? The idea is we're going to have the chair with the affordance and geometrical prompt. Well, then we have lots of different representation by the clip. We'll get lots of the texture encoders. Make sure the chair is going to be, for example, have number of the n attribute embedding, and this attribute embedding is going to be naturally associated with different parts of this object. And then in the meantime, this is also very smart retreated. We have multiple scale at the different patch of the image so that we have a little part because we think the object might be occluded and then they only present a little part. So we're going to represent the whole image with different patch, different scale as well. And then naturally we have this cosine similarity of the geometric and affordance score for each patch. And then we're going to some average to the GA map, which is presented with the which actually reflecting the score for that area have the certain object, like have the certain object. So based on the average of the attributes. So by doing this, we do having a good performance compares to the previous ones only based on object, or we based on the multi-scale object, multi-scaled object and affordance. They do improve the performance of the find out where's the object. Yeah, we are not doing locomotion in these cases. So we're not really trained those locomotion, which means we're not really do this reinforced learning in this case as well. So, and this is a good example showing the ideas for multi-scale, multiple scale for using the patch representations and then gradient-based. We do find out the patch-based representation is going to be it's corresponding better with the saliency of the semantic saliency part. If you look at the gradient-based one, and then it's more or less not better or not well corresponding with the part semantic, whereas the patch one is going to get better corresponding to the saliency of the semantic meanings here. So this is an experiment that even with the most advanced, they're GPT-4V, but they're not capable of find out the part to reason out the whole entire object, whereas our method is going to be working that is capable guiding those on object, like the robot goes to that object. Whereas this GPT-4V is going to simply ignoring that part, goes to living rooms and kitchen room. Their very last task for after the object goal-driven, I think the very important part is going to be instance image goal-driven. So this is required more high standards for locating the object that is you actually just waved with the image. So we're going to see how this work. Assume you're given a picture for this robot before the navigates, how to actually find out the object in this environment. There's two in compared to the object goal-driven. The another important challenging, the not very critical challenging here is the object. It's presented with different views. It's not may not necessarily viewing from a good viewpoint that you're going to find out this environment. So the object might be just given in any views. So we need to find out what is going to be best view to sort of locate an object in the view that it's been showing the object. So therefore, the most important part of course, is going to synthesize novel views of the environment that is going to be naturally matching, align with the views that you already seen this object before. So the best, the ways to the synthesize novel views has the two. One is the for the nerve, the neural representation ones. Another one is very popular used to Gaussian splatting. So I think it's both are working very similar. It's just you have both have a very good compressions representation of this environment, which is very important for nowadays world modeling parts. You need to have a good representations. So 3D Gaussian splatting is relative more lightweight, efficient, but also preserve the fidelity of the 3D environment. That is leading it's rendering faster than this nerve. As you can see, it's going to be I like to render at over hundreds FPS. So, and in this paper, we use the 3D Gaussian splatting as a good ways to representing those compressed 3D environments. So, and so, in order to find out where is this where is the object, so the best, the very previous method is that exhaustively searching the viewpoint, sample, and then do the matching of the pixels. Our methods, instead of searching, exhaustively matching this viewpoint, we are going to be find a way to optimize the viewpoint predictions. Then this is going to be contribution of these papers. So the way we did it's when we do this 3D Gaussian splatting, we naturally integrate those visual encoders infos for those text semantic informations to those Gaussians. For each smaller Gaussians, we do have not only have their 3D representations, but we also have the semantic visual fields representations of their at each Gaussians. So this is very helpful because in the future, when you have query of this certain semantic information or certain visual informations, you could naturally find out which area of the Gaussians might be highly likely be contains the objects that you are looking for at semantic levels. So, and then so the give you example, right? So if you want looking for this instance image goals, and then you have semantic instructions, and then you can easily search on the visual feature field that very quickly find out the possible semantic area like in this Gaussians. So and this it's not necessary always it's not necessary find out pretty accurate where's the instance, but you're going to find a potential area, potential Gaussians that contains this semantic meanings. For instance, for the chairs, you're going to have multiple area, maybe have the chairs. So, but given those area, how you can actually find out where's the instance, then this is going to need a bit more optimal viewpoints estimations. So what we did is we are going to shooting lots of the Gaussian ray casting from this area, from any F area, from all of area. Each area is going to be selecting a certain Gaussian, and then we're going to shooting the casting this views, the rays, and then each one is going to render it with the sort of the affinity, like similarity between this the ray renders and then actually the actual image instance goals. We're going to get this the matchings. So which ray is going to matching with those the image that we're looking for, because we have no idea which area it's going to be. We know it's only possible from those three Gaussians, but it's not going to be. It's not going to know which it's the actual area contained this instance. So after that, we're going to sort of what we did is you're going to using the top ranking rates, for instance, top 10% of the rates, and then using the least square find out where is the intersect of top 10, top 10%. Then it's going to be rendered as a viewpoint, and then they're going to render its object. We find out this is going to be very naturally corresponding with the instance based on probably like 10% of the rays that were based on the ranking part. So this is turned to be very effective instead compares to you just randomly randomly shooting the rays, but we are using those kind of this mechanism, the ranking those top views, and then they're going to find out which one is going to be the actually instance and what is actually viewpoints that we look at this object. It works fine in lots of cases, and then the performance it's good compared to state-of-the-art methods. We do improve. In fact, now we close the performance. If this paper is submitted to one of the conference we just submitted, it's not significantly improved, but now the performance is nearly over the 100. So there's some tricks we have not really added in this paper, but we're going to talking about when it's going to be enhanced as extensive versions. If this paper will accept, it's enhanced to do those journal versions as well. So this is one of the tests. We put it testing this humanoid, and this is one of the robot we had in the lab. The robot, we did a bit more enhancement by adding this LiDARs as well as real sensors, which is not really originally common with this, is not originally common with this humanoids. And then we had this about 300 square meters area where we hide it, this object here. So you're going to see the results. I'll just show you. Yeah, you're going to see there are they want to find out this view here, but they're locating where is the viewpoint on the front. So this is different camera. We see this object finding process. And this is eco views observations. They have another task, so enjoy this demo. It's not that uh, very intelligent robot yet, but the whole searching the strategy is not that it's not optimized. So in this paper, yeah, indeed, that do find out where is the object in the end. So this is the smaller remember the view of the box, the observation view is different from the view that is showing on the instance part. So okay, so we had enough for the show. So let me. I guess the one of the most interesting parts I would like to talk today, even though it's our starting point, is the dreamer. So I do think those is going to be representing the uh, very big area it's to other dreamers, like it's similar to driver dreamers or any word modeling parts. It's going to present very important. It's going to present a very important weight for to enhancing those navigations. So the dreamer model is the principle behind dream models is very straightforward, right? So it's going to be yeah, you are navigating while you are imagining the state, the world state. So uh, transitions using different maybe you can use given those current state and actions. So but the idea is it's well instead of the sort of this only estimating the policy, you have a good policies. If you want to enable the long horizon trajectories, you also having a good ways to estimating those dynamic like world states change. In this cases, we are having a good estimation for the global map. We like every times when when we navigate based on the current observations, we always imagine what it looks like for the whole map. So the strategy of those, you can use lots of those generative models. For example, you can use this BERT for those auto-regression models as well. You can use the diffusions to generate next state representation as well. So even though the one we're selecting, I think it's not performs pretty good. So that's why we need a lot of efforts to work on these parts. And this paper is unfortunately been declined for this time, but at least it's given a good indication for our next improvements of this work. So, but it's at least it's some area I'm very interesting. So they navigating why you're dreaming for next state or the multiple state along the way. It's also very interesting. So there are a lot of the opportunity we can improve these parts, but the key part is instead of only predicting a good policy, you also having a good world dynamic being modeled. So I mean, you can see the results. It's also relatively good, but it's not really as expected. As expected. I think the main reason for this one is when I talked about my students about this. I think the main reason it's because their imagine should be at their local and global. So, but in these papers, they always imagine for the global scales. So I think this is it's something that we should working on to having a good representation only for those kind of like local state transitions. But local state transitions should not be represented as a global map. So that's the things should improve. The very brief summary of those of this talk, it's we talking a little bit brief about the object goal. We talk very heavily about object goal navigations. We're talking about the instance image goal navigations, and then we very briefly, because this is work we have not yet. We just started a few months ago, so even less than a few months ago. So the work is very primitive, and then, but I really think there's a lot of hope to creating average generative models, creating dynamic scene representations, and word modeling parts, enable robust long horizon and planning by representing environment dynamics. So it's only my personal takeaways on embodied navigations. The foundation models in policy learning. I think foundation model, like large language model and multimodal foundation models, do have a good potential for enhancing the policy learning for embodied agents. They provide pretty robust prior knowledge based on this that can be fine-tuned for specific tasks, improving generalization of adaptabilities. But I think this is it's beneficial, but I think it's not strictly essential. So I personally don't really think it is needed or it's necessary to have very strong foundational models. I think the task-specific models can be performed very effectively without them. Take an example for those the pi and the pi 0, pi 0.5, and even for lots of this a very open source VOA models. I think those foundation models essentially is not necessarily be that important in the cases, but for the policy learning, I think it's still beneficial, but it's not going to be, it should not be the focus or heavily research components in this embodied navigation part. I cannot emphasize more of the two following parts. One is the very important world representation learning. So I think learning pretty accurate world representation is very crucial for modern environment dynamics. So it's very important to capture underlying structure and the physics of the environment, enable their agents predicting future states and making informed decisions. This representation should be extremely spatially informed, which means it's not lots of the spatially informed, with lots of the geometry structure should be preserved. So the role modeling with very strong spatial intelligence, I think, is very important. The very last point is, I think it's very important as well. It's physics informed. So if you work in a robot, it's not like you're generating the videos. It's not like you're make it looks pretty fancy. It has to be physics. The representation has to be physics informed. Otherwise, it's going to be better informed agents. They understand predicting new reactions, because the model, the agent is going to be in the end, has to be very nicely interact with the environment, and the environment is physics environment. So in order to not fail, in order to, when you push the door is going to open. Push the door is not going to give a very strong bouncing of the force. A lot of things should be modeled with this kind of word modeling part. This too, I think it's laid out very important foundation to make sure this robot is going to be safely operating in this environment. In a sense, I think the policy learning parts, it's relative straightforward, given those nice policy greens, or those current paradigms learning the policy parts, having those imitation learning, have this SFT, this surprise fine-tuning parts. So all of these things, I think, is relative straightforward, but this word modeling part indeed present a lot of challenging for us to understand. In these cases, I think the smaller or constrained world environmental learning, it's at beginning it's possible, but if you want to scale up, I do think the videos, the internet videos, including the current release by our colleague Yana Quinn for the VJPA, those indeed holding a lot of strong opportunity for us to integrate them to those robotics application part. Yeah. On that note, I would like to acknowledge the Dr. Swan Hong and my students for those embodied navigation work. It's a lot of work, and also for the guitar, he very working very hard to make sure that the experiment is going to be properly conducted. So thank you very much, and then you're welcome for any questions that you have.
Can I ask one question?
Bruce.
Yeah. Thanks for the great talk, and I really enjoyed your talk. My question is, in your perspective, what kind of research should be done in, especially for the vision, in terms of the robotics, when we apply the robotics to migrate the robotics with the vision language model, what kind of research will be promising? So in my perspective, it will be like a personalizations or lightweight network or the retrieval. So is there any content that we have to develop further?
I think in terms of robotics, there's I think at least three very important promising research that at least our lab is working now. It's the cross embodiment. So that's a very important area. So we make our like embodiment embodied AI, including the perception, reasoning, and also the planning parts. It could be applies to those different embodiments. So applying the different embodiments, it's not that it's feasible. I'm saying, and then the different embodiments has its own the action space, and then the action space you need to have a unified action space for the different embodiments by having a good dictionary. One is the discrete dictionary, and one is the continuous dictionary. So how do you have a good VQVAE, this kind of dictionary learning to make sure this discrete and the continuous one be unified is it's very important. And the second, and also the different embodiments have different reward functions when you actually have different local motions when you interact with environments. So that is holding a lot of the challenging for those research. The second part is across different tasks. So I think one embodiment or different embodiments have different tasks. Because different tasks requires different different tasks has different requirements. Then it's always have for the robots is going to be present with it's multitask, multi-environment. So that's going to be a very important research area. For instance, how do you, once you prepare the coffee, how are you going to be actually naturally knowing how to prepare the tea? And also when you're good to riding the bike, how do you good to riding the motorcycles, for instance, right? So this kind of the meta policy should be naturally learned. I think one of the other important parts it's a physics informed. Those things it's always been integrated at the training of the robot, not necessarily for the locomotions, but also for to complete certain tasks. You need to design a nice way to the reward functions, and then that requires a lot of things to integrate with this physics constraint to this reward function design as well. There are a lot of research you can do, but I think the only way I would like to put in here is in order to scale up to have this kind of general purpose robot. It's going to be it's going to be video. Online video is the only way to scale up. Yeah.
Okay, thanks for sharing your great insight.
Yes.
Hi,
Any
Professor Fang, can you hear me?
this is clear.
Yes, I just open question because next presentation, and actually I've been the CVPR this year in the several days ago. We talk a lot about the robotics, but there has two voice. Some people they think, okay, until now we only need 2D images and for the robotics, because if we have the enough images, we only need to train the model because the action is step by step. So that means at the beginning and the action or the direction can be very rough. So they claim we don't need 3D points or 3D data. We don't need any 3D things in the robotic system. But the others, they claim that is because the robotic is in the 3D world. If we really want to know the exact locations or something like that, we have to use the 3D data. So for you, in the long-term goals or in the long-term research, do you think the 3D point is a necessary data or something like that?
This is very good questions. I talked to the author from that. This year is the overrepresentation by the Apple, the general purpose agent. I think that's the one of the papers. It's very impressive papers. but the idea is, I think this the big issues for this one is, I would like to think about three ways. Okay, the first, in order to make it any general purpose or video-based general purpose agent, including robotic agents, the first step is pre-training. The
Okay.
second step is SFT, the supervised fine-tuning. The third step is RL, reinforced learning with reward, with like a feedback or RL validation. This is the reinforced learning's final step. So the pre-training stage, which is self-supervised learning stage, the need 3D information. They have to have that part, which means given any 2D observations, any 2D observations, you have to have it self-supervised, the 3D positions of that corresponding embodiments have 3D positions. Whatever you observed in 3D, it has to be self-supervised learned. Otherwise, those if this corresponding is not learned in the extremely large scale pre-trained stage, it's not possible in any foreign state like the SFT and RL parts. If you remove that 3D, then it's not going to work. Though SFT stage, my personal perspective is we need the 3D as well. So we still need the fine-tuned with the 3D. So the RL for sure. The SFT part, it's going to be more like imitation learning, behavior cloning part. I think it's very important to have 3D spin cloning parts. That is could become from the video demonstrations and also the human demonstrations. So the RL part, it lets the robot actually play by its own within the interaction with the environment. So this is also strongly preferred with the 3D informations that is in order to make sure that a robot is going to be capable pick up that spatial intelligence. So without 3D, I would say if your world model representation has the spatial information, we don't need it. If your world representation do have the spatial representations, that's that is you don't need it those 3D additional 3D observations. So I think the VJPA, the released for those days by the Meta, they do have the 3D representations. Otherwise, cannot be accurately present next state. So to briefly answer your questions, I think we need those 3D informations, the spatial informations, but it's not necessarily been explicitly observed. It could be implicitly as a world representation, not explicitly being say you have to have depth representations, but as long as it's implicitly with this world representations, that's it's going to be safe. Yeah.
Yeah, I definitely agree with your idea. Even in the pre-training or SFT or RL, actually we need our algorithm need to know what happens in the video, what's the objections, what's the aims, and something like that. And if we have the 3D data, we have the accurate and a lot of the 3D data, we can train it. It definitely can improve the accuracy or something like that. Yep. And
Yeah.
but the point is that how can we get the data? It's very difficult because now we talk a lot about the word model, and actually now in the word model we combine the language, image, video, and even 3D now. But no, I don't definitely sure, but I don't think there has a model they combine the robotics in the word model. But actually, same thing, because for the video generation, the prediction is next frame, and for the robotics, and the prediction is the next action. So I think the robotics will be combined or will be merged in the word model, but how to is more complicated than the others.
This is one thing I need to minorly correct it for the robotics. They not only predict their action, they also predict the state transitions. So there's two things has to be there. Otherwise, their model it's only trains policy. They don't train
States.
state. So if you train a state, it naturally integrate world representations. That is very key part. I cannot emphasize more for the world dynamics presentations. There's two things as I mentioned. One is the spatial, like the 3D or the spatial representation that you need to integrate in the state transition part. This is like, for example, the object on the left. If you push the car, if you turn left, maybe the object is going to be your right. So this kind of spatial information, not only for the distance, has to be predicted, and also in physics informed. It has to be there. For instance, you predict a very hard object, you should not go there. It's hard. I mean, if it's slope, it should not slide. So I mean, it's very, very new area. It's a complete open research. I really hope lots of more people get engaged in this area because it's as I said, the policy, prediction, action. This is pretty minor. I mean, our vision people did a lot of things along that lines. I mean, we're predicting the good actions. We have a lot of way to do that, right? So we have VAE evaluations. We're using Gaussian to predicting those actions. We also have this very nice flow models or nice diffusion models. A lot of models could be bounded to this action space, but the world dynamics it's very difficult to predict it. So, I mean, if you guys work on this area, you should look at that area.
Can I understand the state transition is a kind of the interactive with the environments. It's totally different, only prediction or something like that. It's interactive things. Okay, yeah, it's definitely difficult, but we need to solve it.
With the action and how there's dynamic change. It's very more important. So, and this is and the transition. It's actually independent from action, and it's going to be say, well, and because the model, the marginal distribution of the world model, it's fixed. I mean, whatever the work present is not because your push is going to change. It's only things is like if you're translated from the state to another state, it's depending by the action you pushed. So the interaction process. But what is the probability of a certain state being observed? It's actually fixed. It's nothing to do with your actions. So therefore, and then the things that we don't know, it's too big. This is marginal distribution of the world. It's too big. It's really difficult to understand what distribution part. But we do need model that good dynamics, which means when we have a certain action, what its next looks like. This one is very good.
Yes, thank you so much. I really enjoyed talk with you. Maybe in the future, if we find more collaboration with Hao and Cong Cong. Thank you so much.
We should. We're going talking about this a lot. Yeah.
Yeah, I have a simple question. Do you think it's yeah, if we can build a very like a simulating environment to train robots, is this the viable path to leading to a a good robot, just like we train those chess game, Go game, yeah. Because training
This is
robots
possible.
in real world is also very difficult. What if we just totally go with a simulated approach? Is this approach good anywhere to go, or it's totally hopeless?
It's hopeless. So don't think about that line. The only things, the only pathway towards generalized purpose is leverage the videos. So the video is physical world, like the existing videos, like the YouTube videos. I think we need to really understand like how people interact with the environment, and those kind of physics and this kind of the dynamics change. It's indeed like involves all of the world dynamics that we can use so far, and then those it's called real to sim to real video to simulation. Like this is simulations because you train the robot in simulation, but the simulations come from the real videos, real to sim to real. And the real it means after you train your robot, you need to also transfer this embodied intelligence from the simulation to the real environment. So this is going to be a good pathway to scale up training. But if you just simply build on this gaming, this kind of the simulation environment, I didn't see any hope over there. It's hopeless. Yeah.
Yeah, I think this reminds you to simulate the beach view you see in person, to simulate that feeling in a computer, it costs you hundreds, thousands of NVIDIA's most advanced GPU because to simulate the real world, it's way harder than anyone thinks. Yeah.
Nearly impossible. So I think the smaller constrained world environment plus the like this, at least our lab is working on that part. This real to sim to real. It looks like a good paradigms from the real videos, like, and then you capture the dynamics from the real videos, and it goes to those simulation environments. And this simulation environment is built from the real videos, and then we train the robots on that part, and then see if it's humanoid, you see how human interact, and then you put our humanoid models on that human interact environment, and then you translate those sim to real transform. So this, for me, it's good. It's, at least it makes sense. So, but other parts, I feel like it's going to be difficult.
Mm. I'm definitely sure, but I think maybe in the simulation data is easier to find or to learn some physical rules or physical things. Maybe it can help our to transfer the simulation to the real world data. Because at the beginning, if we want to find some physical rules from the real world data, it's so difficult. Maybe it's just the initial or earlier strategy or methods, and in the future, they will move to the real world data. I'm not sure.
Yeah, it's as I said, this is pretty open research field. I mean, no one knows what's going on, but it's holding. I would say next big conference. It's any conference like CEPR, ICCV, in Europe, SASM. You're gonna see many these topics being discussed. It's very new, and then I mean, I think we need some theoretical breakthrough. Yeah, I don't think the current one it's the way, like this kind of the pi zero transformer VOA. I really think that's too. I mean, if you look at the world, it's a distribution of different states, and then you how do you model this distribution is always very difficult because it's the world observation, it's even beyond our human sensory. We only hear the certain range of the signal. Spectrum is very limited. we see a different spectrum. It's very limited as well. How are you going to build a world model that capture all of this kind of state? I mean, I think we need some breakthrough. This flow methods, the current generative model, it's too limited. You sample from the Gaussian. That is where the current diffusion or flow method, right? Sample from Gaussian, and then you are somehow to moving the sample from to matching with another distribution that's for the data. So this is very nice ways, like the diffusion methods and then flow method. It's pretty nice. At least it's working solutions, but I think it's limited. Yeah.
Yes. It's so difficult to find some theoretical things to formulate something. Yeah, it's still a long way to go.
Okay.
Any more questions?
Maybe
If no, let's yeah.
I have a
Yeah, go
small
ahead.
yeah, I hope it's not out of the scope, but for I don't know if I understood correctly, but for gamma, I wonder would be possible to use also geometry information and affordance to do like manipulation or locomotion. I don't know if it's already the case, but yeah, I was wondering, like it's just for object detection that you were using the both geometry and affordance, right?
Now, the manipulation, grasping, they're all very different tasks, like the locomotion, manipulations, manipulation, and grasping is one category, and also navigations. So those especially for many grasping parts, they need a lot of the estimating of the pose. That 3D, like you need estimating the pose of the objects. Otherwise, it's very difficult to grasping that. So that requires a lot of spatial understanding because only you have this, you take a picture, right? It's difficult predicting the whole trajectory of the actions, like how you move, how you different the pose of the graspers. So like they're equivalent navigation, grasping manipulations. So it's just the action space represent a difference. For manipulation and grasping, action space is more continuous space, and navigation is more a discrete space. So
Yeah, okay. Yeah, thanks.
If no more questions, let's thank Dr. Yifang's presentation, and thank you for sharing your latest
thank you.
insights.
Let's just collaborate on that part. Thank you very much.
Yeah,
Thank you very much.
thank you. Bye bye.